Section 1 of The Einstein Theory of Relativity. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in January 2020. The Einstein Theory of Relativity by Hendrik A.Lorentz. Section 1. Note: whether it is true or not that not more than 12 persons in all the world are able to understand Einstein's theory, it is nevertheless a fact that there is a constant demand for information about this much debated topic of relativity. The books published on the subject are so technical that only a person trained in pure physics and higher mathematics is able to fully understand them. In order to make a popular explanation of this far-reaching theory available, the present book is published. Professor Lorentz is credited by Einstein with sharing the development of his theory. He is doubtless better able than any other man, except the author himself, to explain this scientific discovery. The publishers wish to acknowledge their indebtedness to the New York Times, the Review of Reviews, and the Athenaeum for courteous permission to reprint articles from their pages. Professor Lorentz's article appeared originally in the Nieuwe Rotterdamsche Courant of November 19, 1919. Introduction. The action of the Royal Society at its meeting in London on November 6th in recognizing Dr. Albert Einstein's theory of relativity has caused a great stir in scientific circles on both sides of the Atlantic. Dr. Einstein propounded his theory nearly 15 years ago. The present revival of interest in it is due to the remarkable confirmation which it received in the report of the observations made during the sun's eclipse of last May, to determine whether rays of light passing close to the sun are deflected from their course. The actual deflection of the rays that was discovered by the astronomers was precisely what had been predicted theoretically by Einstein many years since. This striking confirmation has led certain German scientists to assert that no scientific discovery of such importance has been made since Newton's theory of gravitation was promulgated. This suggestion, however, was put aside by Dr. Einstein himself when he was interviewed by a correspondent of the New York Times at his home in Berlin. To this correspondent he expressed the difference between his conception and the law of gravitation in the following terms. Please imagine the earth removed, and in its place suspended a box as big as a room or a whole house, and inside a man naturally floating in the center, there being no force whatever pulling him. Imagine further this box being, by a rope or other contrivance, suddenly jerked to one side, which is scientifically termed deform motion, as opposed to uniform motion. The person would then naturally reach bottom on the opposite side. The result would consequently be the same as if he obeyed Newton's law of gravitation, while in fact there is no gravitation exerted whatever, which proves that deform motion will in every case produce the same effects as gravitation. I have applied this new idea to every kind of deform motion, and have thus developed mathematical formulas which I am convinced give more precise results than those based on Newton's theory. Newton's formulas, however, are such close approximations that it was difficult to find by observation any obvious disagreement with experience. Dr. Einstein, it must be remembered, is a physicist and not an astronomer. He developed his theory as a mathematical formula. The confirmation of it came from the astronomers. As he himself said, the crucial test was supplied by the last total solar eclipse. Observations then proved that the rays of fixed stars, having to pass close to the sun to reach the earth, were deflected the exact amount demanded by Einstein's formulas. The deflection was also in the direction predicted by him. The question must have occurred to many, what has all this to do with relativity? When this query was propounded by the Times correspondent to Dr. Einstein, he replied as follows. The term relativity refers to time and space. According to Galileo and Newton, time and space were absolute entities, and the moving systems of the universe were dependent on this absolute time and space. On this conception was built the science of mechanics. The resulting formulas sufficed for all motions of a slow nature. It was found, however, that they would not conform to the rapid motions apparent in electrodynamics. This led the Dutch professor, A.Lorentz, and myself to develop the theory of special relativity. Briefly, it discards absolute time and space and makes them in every instance relative to moving systems. By this theory, all phenomena in electrodynamics, as well as mechanics, hitherto irreducible by the old formulae, and there are multitudes, were satisfactorily explained. Till now it was believed that time and space existed by themselves, even if there was nothing else, no sun, no earth, no stars, while now we know that time and space are not the vessel for the universe, but could not exist at all if there were no contents, namely no sun, earth, and other celestial bodies. This special relativity, forming the first part of my theory, relates to all systems moving with uniform motion, that is, moving in a straight line with equal velocity. Gradually I was led to the idea, seeming a very paradox in science, that it might apply equally to all moving systems, even of difform motion, and thus I developed the conception of general relativity, which forms the second part of my theory. As summarized by an American astronomer, Professor Henry Norris Russell of Princeton, in the Scientific American for November 29, Einstein's contribution amounts to this. The central fact which has been proved, and which is of great interest and importance, is that the natural phenomena involving gravitation and inertia, such as the motions of the planets, and the phenomena involving electricity and magnetism, including the motion of light, are not independent of one another, but are intimately related, so that both sets of phenomena should be regarded as parts of one vast system embracing all nature. The relation of the two is, however, of such a character that it is perceptible only in a very few instances, and then only to refined observations. Already before the war, Einstein had immense fame among physicists and among all who are interested in the philosophy of science because of his principle of relativity. Clerk Maxwell had shown that light is electromagnetic, and had reduced the whole theory of electromagnetism to a small number of equations, which are fundamental in all subsequent work. But these equations were entangled with the hypothesis of the ether, and with the notion of motion relative to the ether. Since the ether was supposed to be at rest, such motion was indistinguishable from absolute motion. The motion of the earth relatively to the ether should have been different at different points of its orbit, and measurable phenomena should have resulted from this difference. But none did, and all attempts to detect effects of motions relative to the ether failed. The theory of relativity succeeded in accounting for this fact, but it was necessary incidentally to throw over the one universal time and substitute local times attached to moving bodies and varying according to their motion. The equations on which the theory of relativity is based are due to Lorentz, but Einstein connected them with his general principle, namely that there must be nothing in observable phenomena which could be attributed to absolute motion of the observer. In orthodox Newtonian dynamics, the principle of relativity had a simpler form, which did not require the substitution of local time for general time. But it now appeared that Newtonian dynamics is only valid when we confine ourselves to velocities much less than that of light. The whole Galileo-Newton system thus sank to the level of a first approximation, becoming progressively less exact as the velocities concerned approached that of light. Einstein's extension of his principle so as to account for gravitation was made during the war, and for a considerable period our astronomers were unable to become acquainted with it, owing to the difficulty of obtaining German printed matter. However, copies of his work ultimately reached the outside world and enabled people to learn more about it. Gravitation, ever since Newton, had remained isolated from other forces in nature. Various attempts had been made to account for it, but without success. The immense unification effected by electromagnetism apparently left gravitation out of its scope. It seemed that nature had presented a challenge to the physicists which none of them were able to meet. At this point, Einstein intervened with a hypothesis, which, apart altogether from subsequent verification, deserves to rank as one of the great monuments of human genius. After correcting Newton, it remained to correct Euclid, and it was in terms of non-Euclidean geometry that he stated his new theory. Non-Euclidean geometry is a study of which the primary motive was logical and philosophical. Few of its promoters ever dreamed that it would come to be applied in physics. Some of Euclid's axioms were felt to be not necessary truths, but mere empirical laws. In order to establish this view, self-consistent geometries were constructed upon assumptions other than those of Euclid. In these geometries, the sum of the angles of a triangle is not two right angles, and the departure from two right angles increases as the size of the triangle increases. It is often said that in non-Euclidean geometry, space has a curvature, but this way of stating the matter is misleading, since it seems to imply a fourth dimension, which is not implied by these systems. Einstein supposes that space is Euclidean where it is sufficiently remote from matter, but that the presence of matter causes it to become slightly non-Euclidean. The more matter there is in the neighborhood, the more space will depart from Euclid. By the help of this hypothesis, together with his previous theory of relativity, he deduces gravitation, very approximately, but not exactly, according to the Newtonian law of the inverse square. The minute differences between the effects deduced from his theory and those deduced from Newton are measurable in certain cases. There are, so far, three crucial tests of the relative accuracy of the new theory and the old. 1. The perihelion of Mercury shows a discrepancy which has long puzzled astronomers. This discrepancy is fully accounted for by Einstein. At the time when he published his theory, this was its only experimental verification. 2. Modern physicists were willing to suppose that light might be subject to gravitation, i.e., that a ray of light passing near a great mass like the Sun might be deflected to the extent to which a particle moving with the same velocity would be deflected according to the orthodox theory of gravitation. But Einstein's theory required that the light should be deflected just twice as much as this. The matter could only be tested during an eclipse among a number of bright stars. Fortunately, a peculiarly favorable eclipse occurred last year. The results of the observations have now been published and are found to verify Einstein's prediction. The verification is not, of course, quite exact. With such delicate observations, that was not to be expected. In some cases, the departure is considerable. but taking the advantage of the best series of observations, the deflection at the sun's limb is found to be 1.98 seconds, with a probable error of about 6%, whereas the deflection calculated by Einstein's theory should be 1.75 seconds. It will be noticed that Einstein's theory gave a deflection twice as large as that predicted by the orthodox theory, and that the observed deflection is slightly larger than Einstein predicted. The discrepancy is well within what might be expected in view of the minuteness of the measurements. It is therefore generally acknowledged by astronomers that the outcome is a triumph for Einstein. 3. In the excitement of this sensational verification, there has been a tendency to overlook the third experimental test to which Einstein's theory was to be subjected. If his theory is correct as it stands, there ought, in a gravitational field, to be a displacement of the lines of the spectrum towards the red. No such effect has been discovered. Spectroscopists maintain that, so far as can be seen at present, there is no way of accounting for this failure if Einstein's theory in its present form is assumed. They admit that some compensating cause may be discovered to explain the discrepancy, but they think it far more probable that Einstein's theory requires some essential modification. Meanwhile, a certain suspense of judgment is called for. The new law has been so amazingly successful in 2 of the 3 tests that there must be something valid about it, even if it is not exactly right as yet. Einstein's theory has the very highest degree of aesthetic merit. Every lover of the beautiful must wish it to be true. It gives a vast unified survey of the operations of nature, with a technical simplicity in the critical assumptions which makes the wealth of deductions astonishing. It is a case of an advance arrived at by pure theory. The whole effect of Einstein's work is to make physics more philosophical, in a good sense, and to restore some of that intellectual unity which belonged to the great scientific systems of the 17th and 18th centuries, but which was lost through increasing specialization and the overwhelming mass of detailed knowledge. In some ways our age is not a good one to live in, but for those who are interested in physics, there are great compensations. End of section 1.